Preparation of an important document which is called Technical Design Report of a detector called Time Projection Chamber, which is the heart of ALICE. Then he led the development of the front end and readout electronics for the same detector, which was adopted in the upgraded version of other experiments, STAR experiment at Brookhaven National Laboratory and the MIPP experiment at Fermilab. This development represents one of the first examples of an integration of an entire mixed signal system in a single chip. This aroused a great interest from industry and elsewhere. In 2006, he was appointed to coordinate the commissioning of the time projection chamber. In 2007, he became the technical coordinator, a position which he held for 4 years, looking after the installation, commissioning of the detector, as well as the first 2 years of physics run at LHC. This detector is the major detector in ALICE, the world's largest TPC, which was made by 100 plus collaborators from 15 institutes. It was such a beautiful detector that its particle identification now finds place in the particle data group. It replaced a 30-year-old plot or more. 2011 to 19, he was project leader of another very important detector in ALICE, inert tracking system. While managing the operation of this inert tracking system or ITS, he initiated studies for its upgrade, and which means that he was part of the editorial board of letter of intent for the upgrade of ALICE experiment, ITS upgrade technical design report, which was approved by the research board in 2012. This detector is a collaboration of 150 people with 33 participating institutes. Because of his enormous technical and scientific knowledge, he has served in several scientific committees, including IPHC Strasbourg, FAIR at GSI, JINR at Dubna. One of his major contribution to the next generation heavy ion physicist is ALICE 3, a proposal for the next generation heavy ion experiment at CERN, which has now received approval of LHCC at CERN. This will enable heavy ion community to carry forward its program at CERN beyond 2030. A great supporter and well-wisher of Indian group, he has proactively looked at young scientists from India and supported their placements at various scientific positions at CERN, outside CERN, and within ALICE. He has also deeply supported the Forward Calorimeter project, which India is involved in the upcoming upgrades in ALICE. With these words, now I welcome Dr. Musa for delivering the Institute Colloquium. Thank you.
Thank you very much, Professor Mohamti, and yes, microphone. And many thanks for the very warm hospitality. It's a really great pleasure for me to be here today. I've been repeating this several times, but let me do it once more. It was really a trip that I had the desire to do since a long time, and it was planned since a long time. And then at the start of the pandemic and many other issues have delayed this till today. So it's really my great pleasure to be here. So today I will be discussing a topic which is a bit across science and technology. So the idea is to show how one of the research topics at CERN, which is the study and characterization of the quark-gluon plasma, it also opens opportunities to develop new detector technologies, but very often with very important innovations, also with respect to what is done in industry, in sectors which are very strategic for society in general. And that's a little bit the type of message I would like that it comes across in with my talk today. But let me start with a few words about the scientific motivation. In general, what we do at CERN is really to study the basic consequence of matter. So what is the universe made of? So what we are made of. And we do that by inspecting matter at progressively smaller and smaller scales. We all know the structure of the atoms, the structure of the nucleus of the atom. And by now we also know that their constituents, protons and neutrons, are not elementary particles, but they are composite particles made of quarks, which are bound together by other particles called gluons. And under ordinary conditions of temperature and pressure, indeed, these quarks, they're never observed in isolation. They're always confined inside protons and neutrons, or more exotic particles, which we call hadrons, from the Greek word hadros, which means strong, because the force that is responsible for their interaction is the strong force. Why does this happen? In very simple words, well, this is called confinement, and is due to the fact that actually the interaction potential between a quark and antiquark pair, contrary to what happens, for instance, with the electromagnetic force, it actually increases when you increase the distance, okay? So such that a new quark-antiquark pair is created once the energy of the interaction is above the production threshold for a new pair of quark and antiquark particles. So essentially, it is energetically more favorable to create a new pair of quarks and antiquark then further increasing the distance. And that is what leads to this phenomenon, which is one of the distinctive features of the strong interaction, which is called confinement. Now, then the question is, what happens, however, if we put together these particles, hadrons, in a volume, and we try to pack several of them in the volume which is typically occupied by a single hadron. At this point, then the quarks, the constituent particles of the single hadron, they cannot distinguish anymore to which hadron they belong to. So one can already have this very imaginative type of picture where possibly quarks then they should be free to roam in a larger volume, okay? And now from the theoretical point of view, so the strong interaction is described by a beautiful theoretical framework theory, which is called the quantum chromodynamics, which is characterized by a coupling constant, which is essentially characterizes the strength of the interaction, which depends on the momentum that is transferred in the interaction between a quark and antiquark. So this is a running coupling alpha s of q squared. So essentially what happens is that at very short distances, when the quark and antiquark, they exchange a large momentum, you see that the strength of the interaction tends to vanish. And then we are in a regime where actually the equations that describe the quantum chromodynamics can be resolved perturbatively with an expansion to higher orders of this running coupling. On the contrary, and we can therefore give very precise predictions. On the contrary, when we go at large distances and the momentum transfer between the two interacting quarks is very small, alpha s is very large, and therefore a perturbative approach doesn't work. Now, there are different ways of approaching the problem. One which has been very successful, also thanks to the availability of large computing power, is the so-called lattice QCD, where essentially the continuum space-time is mapped into a lattice, and the quarks are mapped into the size of the lattice, and the gluons represents the link of this for the reticle, for the lattice. And then somehow this can be resolved numerically. And if we do that, so this is an approach which works to resolve a static problem. We can study this as an extended system of quarks and gluons, as if we would be treating a condensed condensed matter of quarks, condensed quarkonium matter. If we do so, we actually discover that if we hit the hadronic matter, so there is actually a certain point at transition from a state where the quarks and gluons are confined inside hadrons into a state where they become free. They're not localized anymore into a specific hadron, but they're free, forming the so-called quark-gluon plasma. Now, this diagram that you see here has on the vertical axis the temperature. On the x, you see the baryon density. So that is essentially the difference between protons and antiprotons. And the regime of that is being studied at the LHC, but also at the relativistic heavy ion collider at the Brookhaven National Laboratory in the US, is the one where the baryon density, so where there is an equal abundance of baryons and antibaryons, so matter and antimatter. And so it essentially goes tends to 0. And so we are really in this regime, where indeed the lattice QCD provides the prediction that at a temperature of the order of 1.8 times 10 to the 12 Kelvin, quarks become deconfined and we form a quark-gluon plasma. Now, so if we discuss this as a thermodynamic system, then we can measure its typical thermodynamic properties, as for instance, the pressure of the system, the energy density, the entropy density. And you see these quantities plotted as a function of the temperature. And we really see that there is a critical temperature for which actually we refer to as a pseudo-critical temperature, because as you've seen in the previous plot, there is a sort of a continuum crossover from one state of matter to the other one, and not a real phase transition. So there is a sudden increase of all these quantities, which is essentially signaling that the system has a sudden increase of the number of degrees of freedom. But the reason why I'm showing this plot is to show that even when we go at the largest temperature that we can achieve in the laboratory, let's say of the order of 400 MeV, you see that these parameters, for instance, if we take the energy density, they never reach the limit of a non-interacting gas, so the Boltzmann limit, but they are below. And this is actually has some profound implications, because it's telling us that even if the quarks are deconfined, they continue to be strongly coupled, they continue to interact. And so therefore the new state of matter that we're creating, at least for these values of temperature, will behave as a fluid. Actually, it turns out to be a fluid with a very low viscosity, the lowest attainable set by first principles. Okay, so with this very brief introduction to the main topic of our research, let me add that this is also very interesting for the connections to cosmology, because it is thought, it is conjectured that the quark-gluon plasma represents also the state of matter which existed in the early universe immediately after the Big Bang. for a period of about 10 microseconds in the early instance. And then the system started expanding, the temperature dropped, and below the critical temperature, and then quarks started forming the hadrons, protons, and neutrons, and then progressively, of course, we had nucleosynthesis, atom synthesis, and et cetera, all the evolution of the universe till the way we know it now, and we can observe it now. Now, the question is, can the quark-gluon plasma, apart that we believe that it was the form of matter in the first instance of the universe, can be created, or does it exist in nature? Well, again, we believe that is also the state of matter in dense neutron stars, at the core of dense neutron stars, but we can create it in the laboratory. And one of the laboratory where this is done, actually at the present, this is done essentially in two places in the world, at CERN, which is the European Center for Particle Physics, and at the Relativistic Heavy Ion Collider in the US. So CERN is the world's biggest laboratory for particle physics. It has quite a broad program. And really, in simple words, our goal is to understand the most fundamental particles and laws of the universe. You see in this aerial picture, the location of the laboratory. What you see here is the, let me use the pointer, is the Lake of Geneva. So it's located very close to Geneva. What you see here is the airport of Geneva, and that's the city of Geneva around the lake. And this white ring represents the largest accelerator we have now. It's called the Large Hadron Collider. And it's placed, it's located across the border between Switzerland and France. So this red line is the border between Switzerland, which is on the right side of this picture, and France, which is on the left. It is a laboratory which was founded in 1954. Originally by 12 European member states, and then progressively the geographical scope has been enlarged. We are here a few years after the end of the Second World War. The European states have been fighting a devastating war with many of the scientists that left Europe. Some of them also because persecuted by the racial laws. And so the idea of the founders of the laboratory was to have a laboratory where all the scientists could work together, inspired by the ideal of science for peace, but also to put together the energies in terms of resources that are needed to build large facilities and have a particle accelerator to compete with the United States that in the 50s was leading particle physics. By now, we have 23 member states, and we have 10 associated member states, and we are very proud to have India as a very important partner, as an associate member. But we also have cooperation agreements, international cooperation agreements with more than 50 states and territories. Okay, so it's a very, very large community. It has an annual budget of 1.2 billion, which is essentially the budget of a medium-sized European university. And we have a core staff consisting of about 3,500 employees. The large majority are actually engineers. We have about 1,000 physicists. In my department, there are 600 physicists, but the vast majority are then engineers in the experimental physics department. And what is really important to outline here is that there is a very large community of scientists, close to 13,000, as you can see here, which are coming from all over the world to carry out their research at CERN. So, the basic tool I already anticipated that is the Large Hadron Collider, which is a 27 kilometer accelerator, which is located about 100 meters underground. and is made mostly by superconducting magnets that steered the trajectory of the particles, steer the particles around the ring. And as I will show better in a moment, so essentially particles are accelerated to close to the speed of light. So essentially they reach, protons are accelerated until they reach a velocity of 99.9999991% of the light speed. And so they make 11,000 turns per second. This is also the coldest place, or one of the coldest places in the universe. The temperature inside the accelerator is 1.9 Kelvin. And for this to work properly, the particles have to be accelerated in vacuum. And we have a vacuum in the beam pipes of 10 to the minus 13 atmosphere. Okay. So now so imagine you have two beams of particles which are accelerated in opposite direction. And when they reach the speed of light, then they are passed across. Okay, so they collide. And around the collision points, and they do so in 4 points, and around those points, then we build very large detectors, experiments, which are called Atlas, CMS, ELIS, and LHCb. Now, the number of collisions produced every second is about 1 billion. So essentially, you will see this also in an animation in a moment. The particle beams are structured in bunches. Every bunch has a length of about 30 centimeters. It contains about 10 to the 11 protons, and they are spaced, the various benches are spaced by 7.5 meters. And every time they cross, essentially they cross every 25 nanoseconds. There are about 25 protons which have in these two bunches which cross an inelastic interaction. And so this results therefore in about 1 billion of collisions per second. Now the energy of the particles, so the two, each proton has an energy of 6.8 trillions of electron volts. And this amount of energy that is released in the interaction, so 13.6, then is converted into generation of new particles. And the detectors then they study the many particles which fly out in all possible directions, study their properties, and trying to infer the type of physical process that takes place when they interact. And now I have here an animation which gives you a bit of a pictorial view of how this works. So starting from the location of the laboratory in the center of Europe, in Switzerland. And you see here again the Lake of Geneva is separate, the LHC accelerator, the location of the 4 experiments, ALICE, ATLAS, LHCb, and CMS. And now we are looking at how the particles are accelerated. Actually, this is a complex of a sequence of accelerators that progressively increase the energy, starting from a linear accelerator, then a proton synchrotron, then they are injected in the super proton synchrotron until the energy reaches 400 GeV, and then they are injected into the Large Hadron Collider. And if now we would look at the one of the experiments here now is the Atlas experiment, but this is the principle of operation of also all the others. You see the bunches colliding at the central, the axial center of the detector. You see the bunches every 25 nanoseconds. There is a collision of 2 bunches. They produce many particles that they fly out. And 25 nanoseconds is also the time it takes to the particles to cross our detectors. Okay. So that is just to give you a better idea of how that actually works. Okay, so, and ALICE is one of the 4 experiments. It's an experiment which was conceived and optimized for the study of the nuclei of heavy atoms. And as Bedanga has anticipated, at present we have about 2,000 members coming from 174 institutes from 40 different countries. The experiment was proposed in 92. It was approved in 97, and the bulk of the construction took place in the period 2000-2007. The installation was completed in 2008, and then we are now taking the data, analyzing the data, and producing physics results since 2009. And we had the first campaign, which was completed in 2018. We then had an upgrade of our detector, a massive upgrade in the past 3 years. And now we started a new physics campaign with a much more, with a detector with improved capabilities, both in terms of precision of the measurement that it can perform, but also in terms of the number of collisions that it can inspect per second. Now, India is a major partner of the ALICE collaboration since its inception. At present, we have 14 institutes from India participating in the ALICE program. It's a program which is funded by the Department of Atomic Energy and the Department of Science and Technology. And when I say a major partner, I really mean that. Essentially, it covers in a very prominent manner all the different aspects of the experiment, certainly the physics, with physicists from the Indian institutions that have covered the leading positions, but also in the development of detector hardware, electronics, computing, and data analysis. And here I have just some of the pictures that marked some of the major contributions of India to ALICE so far. With the development of the photomultiplicity detector, which is an Indian flagship project, a very important contribution to the construction of the muon tracking of the muon spectrometer, which is another very important project, and more recently, the common readout unit, which is part of the upgrade. So that is a system that is used to read out essentially all ALICE detectors, was developed and financed by India. And now there is in preparation of a new detector called Focal, where the Indian institutes are providing a very important contribution. So I've shown that the LHC collides protons, and I've also mentioned that it collides the nuclei of heavy ions. So far, we've been colliding lead atoms. Is what can we learn from these collisions? Now, I mentioned before that the QGP is expected to be formed when we exceed a certain temperature. I mentioned that we can study such a system with the lattice QCD, and lattice QCD makes the prediction that the QGP is formed when we have an energy density exceeding 0.4 GeV per cubic Fermi, or a temperature of about 156 MeV, which corresponds to 1.8 times 10 to the 12 Kelvin. By the way, incidentally, let me mention that this is 5 orders of magnitude higher than the temperature at the core of the sun. So now the question is, can we reach these conditions at the LHC when we collide lead nuclei? Well, first of all, the idea, why do we do that? I mean, the idea is that if we, instead of colliding single protons, elementary protons, we collide heavy nuclei, then we have a nearly simultaneous collision of multiple collisions in a very tiny volume, okay? So in a very small volume, we can concentrate a very large amount of energy. And energy, amount, concentration of energy, which to some extent we can vary, let's say by varying the geometry of the collision, or by colliding a different species or different systems. Now, I will show in a moment that unfortunately we cannot have a direct observation of the QGP. We will see in a moment that the QGP has a lifetime of the order of 10 to the minus 23. So we can't have an external probe that we're able to use to directly measure the property of the QGP. So we rely on the emerging particles as probes. Okay, so now when the two nuclei are accelerated due to the Lorentz boost, essentially what we would see in the laboratory reference system are two disks, very thin disks, where each disk has a diameter of about 15 Fermi, and a thickness of 15 Fermi divided by gamma, where gamma at the LHC energies is 2,500. So this is an extremely thin disk that then they pass through each other. Okay, but not always this collision is a head-on collision, so not always they overlap. Actually, most of the time they don't. And the distance between the center of the two nuclei is what we call the impact parameter. And we refer to central collisions when the impact parameter tends to 0, and we talk to semicentral or peripheral collisions when the progressively impact parameter increases until it becomes comparable to the radius of the nucleus. We are also very interested in collisions, or better, when the two nuclei actually miss each other. We refer to them as ultra-peripheral collisions. So what happens? You see here again depicted in a very simplistic way in this diagram. So essentially, when the two nuclei they pass through each other, they release a large amount of energy in a very small volume, and this forms the quark-gluon plasma. Very often we say with the terminology which is completely improper and not rigorous that protons and neutrons are melt. Actually, that is not what happens, because actually they escape. But the amount of energy which is released creates matter which is deconfined. And then it expands, progressively expands. You know, there is like an explosion. And when it expands, it starts diluting, of course, but also the temperature reduces progressively till it drops below the critical temperature. And then at this point, quarks and gluon, the quarks, they recombine, forming hadrons. And the relative abundance of the different particle species is fixed at this point. We refer to it as the chemical freeze-out. And then, however, they continue to have interactions. So the hadrons continue to interact. So that is the hadronic phase. Till a certain point, the system is so diluted that there is no interaction anymore. And so also the momenta spectra are well defined, and we refer to it as a kinetic freeze-out. And then the particles that fly, where their characteristic momentum spectrum crossing our detectors. And please note here the time scale. So the QGP is formed very rapidly in the time scale of about 1 Fermi over C. Then it expands, and the full process till the kinetic freeze-outs take a 10 Fermi over C. And then the particles reach our detectors in a time scale of 10 to the 15 Fermi over C, okay? So that's why I said before, you know, it's a very indirect measurement. We're not really observing the QGP, but we're looking at the particles emerging from the QGP at a much later stage. Okay, so in these first 10 years, we did a very broad characterization of the properties of the quark-gluon plasma. We've published in about 400 papers on the topic. Now, as I said, it is not my intention also, this would be too technical to review the results achieved so far. I will only give a few examples now just to give a bit of an impression of the type of studies that are carried out. Now, the first question one would ask is, okay, you claim that you know, QGP is formed when you have a certain energy density and temperature, but do you really achieve these conditions in the collisions of heavy nuclei. And indeed, we have measured the energy density, we measured the temperature, we measured the lifetime volume of the system. Now, all these measurements are still to be refined in order to have sufficiently precise results, and especially in particular, we have here also to rely on proper theoretical modeling of the expansion, the hydrodynamic expansion of the system to properly infer these results. But let's say we are very confident that the conditions are achieved and surpassed, because as you can see here, we estimate an energy density of 12 GeV per cubic Fermi. We measure the temperature by measuring, for instance, the electromagnetic radiation that is emitted by the source. You can regard this as a heat source, so it's emitting electromagnetic radiation. And by measuring its spectrum, we can actually measure the temperature of the system. So that is an effective measure, temperature measured over the full lifetime of the QGP. We will do better in the future, but we measure a temperature of 300 MeV. So we're talking really values which abundantly exceed the critical values. And we also have a measurement of the lifetime volume. You see it as a typical volume of 10-15 Fermi over C. Now, I've been talking about the expansion of the system. What do we mean with that? And in particular, also have been mentioning another keyword, the fact that it behaves as a fluid, as a strongly coupled system. Well, essentially, the fact that they continue to have an interaction. So if there would not be any interaction, once we have the collision, we form a quark-gluon plasma, then the quarks would flow isotropically in all directions, and the hadrons would do the same. Now, the fact that on the contrary, it's a strongly coupled system, this gives rise to a collective motion of the particles, which is superimposed to the thermal motion. And there is this isotropic radial flow, which is indeed a consequence of any interacting system expanding into the vacuum with a common velocity field. And I will show to you what the measurements show. But also very interesting, if we have a collision as represented here, so where they only partially collide, so the collision region has this almond shape. So the fact that this is there is a pressure gradient, so the system is behaving as a fluid. So this converts the special anisotropy into an anisotropy in the momentum space, okay? And so we should be able to measure then an anisotropy of the momentum of the particles that emerge. And we do that by measuring the Fourier expansion, by measuring the harmonics of this Fourier expansion. Now, this is the measurement of the radial flow. You see the empty symbols represent the measurements done in elementary proton-proton collisions and in lead-lead collisions are the measurements done, so are the symbols which are full, okay? And you see three set of curves for ions, kaons, and protons, which are particles with progressively a larger mass. And what we see is indeed that due to this common velocity field, actually when we go from elementary proton collisions to lead collisions, there is a mass-dependent boost. Mass-dependent means that this shift is larger, the larger is the mass of the particle we are looking at. And all these things can be modeled with relativistic hydrodynamic, and there is a very good matching between the experimental results and the models. And here is the anisotropy, the elliptical anisotropy. So we are looking at the second coefficient of this Fourier expansion. And again, we do measurements. So here we're looking at this second coefficient. If there would not be a common flow, this elliptic flow, essentially one would expect to measure here a second coefficient which would be equal to 0. So we measure a value which is not equal to 0, but very importantly, there is again a mass order in the low PT region, and then in the high PT region, there is again a separation depending on the number of quark constituents, which is what one would expect if we would properly model such a system. This is just to show to you that we have an understanding of how the system expands, and the experimental results can be described with the theoretical models. Now, I mentioned that we do not observe directly the QGP, and ideally one would like to realize, like a Rutherford scattering experiment, where you have to characterize a certain structure, for instance, the atom, and then you shoot a beam of some probe. In that case, was half particles, and then by measuring the angle of the emerging probe, you infer the properties of the object that you're studying. Now, unfortunately, we can't do that way for the QGP, but it turns out that quarks with a very large mass, or in general, highly energetic partons, they can actually give us an equivalent mean. In particular, heavy quarks are particularly interesting because they are produced in short distance processes with a very large momentum transfer. So we can calculate them perturbatively. So we know how many we produce in each collision. They are formed very quickly. The time scale is of the order of 0.1 Fermi over C, so before the formation of the QGP, and they have a lifetime which is much longer than the QGP lifetime. So they essentially go across the QGP throughout its evolution. And so we can use them as a probe to study the properties of the QGP. Let me also mention that at the LHC, these probes are produced in large quantities, which of course is particularly important. And again, I will go very quick here. Also, we have been measuring then what happens with these probes. In particular, we measure at the how many the momentum spectra, how the momentum spectra of hadrons which contain a heavy quark are modified when we go from elementary proton collisions to the collisions of heavy nuclei, where we expect the QGP to be formed. And now, what you see in this plot on the right is the nuclear modification factor, which is essentially the ratio of the production yield. So the number of hadrons that are produced in lead-lead collisions with respect to the corresponding number in proton-proton collisions, multiplied by the number of binary collisions that one has. So if you want, one should expect this RAA to be equal to 1 if there is no QGP. And indeed, we see that if we collide a proton with a lead nucleus, indeed, we get a nuclear modification factor, which is about equal to 1. But if we start producing collisions from peripheral to progressively central, we see that the nuclear modification factor is largely suppressed, okay? And then, of course, one can go into a much more detailed studies. And what is extremely exciting, at least from my perspective, is that we have reached, on the experimental side, a level of precision in these measurements, but also on the theoretical side, a very detailed microscopic modeling of the propagation of heavy quarks in the QGP, that now we can have really a comparison between experiment and theory and infer properties as, for instance, the diffusion properties of heavy quarks in the QGP. Okay, so now maybe I skip this. Let me now completely change topic. Well, it's related to that. And talk about the technological challenges, okay? And we do that by taking an example, of course, I've picked up an example that is particularly dear to my heart, but also that I believe that is particularly prominent also when looking at the future of our field, which is the role that the silicon trackers play in high energy physics. And I do that by showing this picture, which is a picture, it's the display of a single collision of two heavy nuclei. Now, of course, here we have the colleagues from CMS. I could have also taken the collisions recorded by CMS. The picture is also very complex. The difference is that instead of having a single collision of two nuclei, you have many proton collisions which are also superimposed, happening within the same bunch crossing. So this is just to show to you all these colorful lines represent the trajectories of charged particles. You see that is an extremely complex pattern, and that becomes particularly dense and intricate when we go to the collision point. And the task of our detectors is to resolve such complex picture, such that we can measure the properties of each of these particles, including at the point in space where they've been originated, okay? So most of them, they're originated in the point where the two protons or the two heavy nuclei, they collide, but many of them are actually the decay products of particles which have a very short lifetime. I've been speaking about heavy quarks, for instance, hadrons which contain heavy quarks. Some of them, they have a lifetime of the order of 100 microns. We are particularly interested in measuring them. So you see this particle is called the lambda C, has a proper decay length of 60 microns, and then it decays in many different ways. It can decay, for instance, in a pion, proton, a kaon. And we cannot put our detector at 60 microns. The closest we can go, and that is done at the LHC in Alice, is about 20 millimeters. So which means we don't see the lambda C, the mother particle, but we see the daughter particles, okay? And then we have to reconstruct their trajectory and extrapolate them towards the interaction point and be able to say whether actually they're coming from the interaction point or from a point that is displaced by 60 microns, about 60 microns from it. Okay, so this, then you immediately combining the previous picture with this information, you immediately realize that to solve such a complex task, we need detectors which have a very high granularity and a very high spatial resolution, right? I mean, otherwise we would not be able to resolve these complex pictures and measure their properties with high resolution. And this task is accomplished by silicon trackers, which are at the heart of all LHC experiments, and I would say of all modern high energy physics experiments. You see here pictures of giant silicon detectors installed in Atlas, CMS, ALICE, and LHCb. And all this rely on technology which have been essentially developed to solve this specific problem, okay? We use silicon strip detectors since the late 70s. We use hybrid pixel detectors since the 90s. In particular, hybrid pixel detectors have been really developed for the LHC experiments, but they are not really the detectors, the high resolution detectors that we find in commercial components. And some time ago, the community started thinking about why not? Why can't we use the sensors, for instance, the pixel sensors that are used in for the imaging of the visible light? Okay, so the sensors that are in the cameras of our mobile phones. Okay, but there is clearly a tremendous development. And you see in this picture the anatomy of a single pixel. So that's really the way they are done. It's not a simplification. So you see here a single pixel. In modern cameras, pixels are the size of 1 micron by 1 micron. or better. There are a few cameras which go down to 0.7. And a quarter of the pixel, can be a little bit more, but let's say about a quarter, is the photodiode. So this is an NP junction. You have the sensitive layer is a very shallow, high resistivity layer of about 5 microns, which is sufficient to absorb the light in the visible range. So the principal operation is that here you create, there is a built-in potential at the junction. And essentially when you have a photon diode, and this, which is accumulated photon diode, is first converted into a voltage by a transistor. You see, the surrounding is a very simple object. Essentially, there are 3 transistors. There is one which transforms the charge into a voltage signal. There is a transistor which, once we have finished to integrate the image, resets the photodiode, so brings it back to the initial state. And the third transistor is used to shift the information into the periphery. In our digital cameras, the pixels are organized in rows and columns. And essentially, the idea is that all the pixels of one row are shifting their signal through the column at the same time. This is called the rolling shutter. You read one row at a time, and the exposure time of the camera is the time it takes to roll over the full matrix. Okay, and then you start again from scratch. And well, it's a little bit more complex than that, but not technologically, not much actually. So because you need filters, so you have this different type of dyes that are used to pass either the red or green or blue. And then there are these small menisc or lenses, micro lenses are called, which help in concentrating the light towards the photodiode. But they work very well even if you remove those. Okay, so it's clear part of the optimization. Now, inspired a bit by that, actually, I would even say that the development of these objects was done in parallel by high energy physicists and in industry. In the 90s, actually, we were among the first to start building some of these devices. And in the industry, they were starting developing toy cameras, cameras for toys for children using these devices, okay? And then in 10 years, they completely took over the market. And by now, essentially 95% of the cameras are based on CMOS sensors and not anymore on CCDs. Anyway, inspired by this, we developed our particle detectors. So the principal operation is very similar. However, with a few important differences. First of all, the sensitive layer is thicker. We have about 25 micron of silicon. So, and we have also an NP junction. So you see this volume here is the volume which is depleted from majority carriers, meaning that here there is electric field, outside there is no electric field, okay? So when a charged particle crosses the silicon, it leaves a trail of electron and holes. And then the interfaces are built such that the electrons and the holes, they cannot escape into the surrounding structure, but they're always confined. It's like if it would be a silicon chamber, okay? So they would bounce back at the interface, as you can see here. So they wander around by diffusion. And then when they reach, at a certain point, each of them will reach the region where there is electric field, and then they are collected by drift, okay? So they move by diffusion, and as soon as they enter the depleted volume, then they are collected by drift. By the way, we can control the depleted volume. Depending on the application, we can make it smaller or larger. We can also reach full depletion, okay? So now the charge collection efficiency is very high, essentially 100%. And the collection time is also very quick. Depending on the size of the depleted volume, we can go from, let's say, 25 nanoseconds down to a fraction of a nanosecond, okay, when they are fully depleted. This is representation of a cutout of a 2 by 2 pixel in the sense that there are 500,000 pixels like that. And you know, what you see below is the 25 micron of silicon and the depleted volume. And what you see here is actually a real picture taken with an electron microscope of the electronics on top. So these are about 10 microns of you know, metal layer, silicon dioxide, all what you need to. And you see the diode is this tiny dot at the center of this black square. It's extremely small diode. It's a 2 microns essentially by 2 microns. And this is extremely important because this results in an extremely small capacitance. And it's the main advantage with respect to hybrid pixel detector of silicon strips, which are characterized by very large capacitances. You know, we are talking about microfarads for strip detectors, and we talk about nanofarad for pixel detectors, okay? Which means that even if we produce a very tiny signal, let's say for a minimum ionizing particle, we get here about 1,300 electrons, this already produces a very large voltage signal at its output. So very interesting objects. And the other main difference with respect to the cameras for visible light, in particular those that we take, you know, we use to take pictures in our daily life, is that those are too slow for us. And so we have to integrate in the matrix a very complex circuit. So what you see, all this colorful region, and so these are, there are about 500, 600, 700 transistors per pixel. In the digital cameras, you have typically 3 or 5 at the most, okay? So that's the difference. And that, of course, we had also to resolve another problem to isolate the electronics with respect to the sensitive layer. Okay, so so this is the building block of a detector, which is the largest pixel detector ever built. We call it inner tracking system. It consists of 12.5 billions of pixels. It has an active area of 10 square meters. So 12.5 billions of pixels, each measuring the spatial resolution of the particles crossing it with a resolution of 5 microns, okay? And they can sustain a very high particle rate. Now, this was developed for the ALICE experiment, but is presently being used by many other projects. You know, we have produced sensors for 20 different projects here. I'm only showing some example. There is the S-Phoenix experiment. There are various experiments by now using this technology, but also we use it for proton CT. I will show a few things about that. And they're also used in satellites for measuring protons and electrons at low energy as a way of monitoring the seismic movements of the Earth. Okay, so here I show to you a small, again, another animation just to give you an idea of, so we start from a silicon wafer. Then this has to be diced, so these individual sensors have to be singled out. Their thickness is reduced to 50 micron. They contain 500,000 pixels, so then we dispose interconnection balls on their surface because they have to be interconnected to an electrical substrate, which is, by the way, also a very lightweight object. Is a flexible Kapton cable with aluminum as conductor, as you can see here in this animation. Then this hybrid structure is mounted on a carbon fiber support structure. So we use the same materials used in aerospace because we have to reduce the mass of our detectors. Then this staves, they form barrels, layers, and then these objects are mounted around the accelerator beam pipe, very close to the beam pipe. Okay, so here you see again representation of how they're inserted. Essentially, it's two halves that are mounted around the beam pipe, okay? And then a large composite structures to carry out power signals and other services. Okay, I think that's the, all right. So this is a picture of the object as built. This is the inner barrel. So these are the elements that go at 20 millimeters radial distance from the beam pipe, from the beam line. And this is the outer barrel. So here we are at 45 centimeters from the beam line. So this detector, it took us about 8 to 10 years to develop and build it. And oops, sorry. And it was successfully installed last summer in the experiment, and it's successfully taking data. We see here one of the first collisions recorded this year. Apologies for the label. Actually, 13.6 TeV and not 13 TeV, as indicated there. Okay, so we are now in the process of preparing the future. We have in our plans 2 detectors to be installed in the around 2027. I already mentioned the focal because it's a project for the calorimeter, which involves the Indian community at large. A very important development, also very innovative. Again, it's the first detector into operation which combines silicon pads and silicon pixel to achieve a very high capability to separate clusters generated by photons emitted at a very small relative angle. But in particular, we are preparing a plan to install at the LHC a completely new detector. We call it ALICE 3 to refer to the 3rd phase of the ALICE experiment. And that's a very exciting program where we will make use of the most advanced technologies. A lot relies on silicon sensors. Yeah, here just, I don't have the time, but I just want to show 2 examples more as a curiosity. This one is the silicon pixel detector. So again, the one closest to the beam line. And here we really are making, again, another step forward in the development of the technology, because for the first time, we will have a pixel detector, which is as large as the entire wafer. So imagine a wafer, which is a diameter of 12 inches. And instead of making chips, which have the typical size of the field of exposure used for the fabrication of circuits. I don't know if you have ever wondered why the chips have always the size of a few square centimeters, okay? That's limited by the field of exposure used for the projection of the processing patterns. And for the first time using a technique which is called the stitching, we will be able to have a chip which is as large as the entire wafer, okay? And then we reduce the thickness to about 30 microns, 40 microns, and then we will be able to wrap this chip around the beam pipe, giving a cylindrical shape as is indicated here. And the R&D on this is quite advanced. Now, the other challenging aspect of this project is that this will be installed inside the vacuum chamber. So it has very complex mechanics to ensure that this can be brought close to the interaction point only once the beams are at the top energy, and so they have an emittance of a maximum millimeter. The other example I wanted to mention is the time of flight detector, because here we are leveraging a development which is done by Atlas and CMS, well, which has been done by the community and will be used for the first time by Atlas and CMS. So this is for the measurement of the time of flight detectors, the time of flight of particles. And the idea is that essentially in a sort of pixelated detector, silicon detector. You introduce a gain layer, okay? So essentially you create a structure which generates a very large electric field such that the electrons, when they come close to that structure, they are accelerated and then can produce again ionization themselves. So there is an avalanche process, but they are operated in avalanche mode with a gain of about 20-30, okay? And this again, they are fabricated as a custom devices, and then they are interconnected to an external readout chip. And what we're planning to do for Alice 3 is actually to build, again, a CMOS sensor where we integrate electronics and sensor in the same chip, essentially using, inspired by the single photon avalanche diodes, which are used in 3D cameras nowadays, okay? And these objects have a time resolution better than 20 picoseconds. Okay, so I've just the last few slides. Now, I mentioned several times already in the introduction that CERN is, of course, is a laboratory to carry out fundamental research in particle physics, but is also a laboratory where we do a lot of technological innovation and development, which have applications in many fields. Maybe some of you know that CERN is the birthplace of the World Wide Web, but there are many more examples which maybe are less known, in particular in the field of medical imaging, cancer therapy, material science, cultural heritage, aerospace, automotive, environment, health and safety, and industrial processes. And here to give you just a few examples, the accelerator technologies that we developed are routinely used in and applied in cancer radiotherapy. CERN has coordinated the TERA project, which led to the hadron therapy, which has now been done at several centers worldwide. So where the tumors are treated, irradiated with protons and ions. It's also the laboratory where the PET was developed, so for medical imaging and diagnostic. The pixel detector technology developed by the community is used for high resolution 3D color X-rays imaging. And also we developed technologies that we continue to carry out with the Isolde facility research and for the development of innovative radioisotopes for nuclear medicine research. And here now, as an example, since I've shown the pixel sensors, right? I mean, one will say, well, show to us practically how do you use one of the technologies in an application outside particle physics. And since I took the CMOS sensors, I showed to you how they can be used for what we call medical tracking. Let me say, first of all, the hadron therapy. Maybe many of you know that the tumors are typically irradiated with X-rays. Now, the most advanced machines are called the CyberKnife machines, meaning that you have many beams crossing the tumor with many different angles. And you may wonder why. And the reason is that if you look at the ionization, the energy loss, the relative dose released by an X-ray beam and in the skull, for instance, of a person, this is actually for water, okay? But it's very similar, it's very representative of the tissues in the head of a patient. You see that there is a dose which is irradiated along with a very shallow type behavior along the full path crossed by the beam. So if you want to deposit the energy in the tumor, then the only way of doing it is to have many beams with the different angles which cross at a given point, such that you release a bit of energy in the full volume of the head, but most of it in the region of interest. Still, this produces a lot of collateral damage, very well. And what's the advantage of using protons or ions? Well, is that the mechanism for energy loss are different, and it's characterized by the Bragg peak. So most of the energy is released in a very small part. Yes, and we can actually tune the position of the Bragg peak by adjusting the energy of the beam. So if we know what is the position of the tumor, we can actually aim at its position such that it's really released there. Okay, but to do that, we need to know the density of the tissues which are around the tumor, because of course the beam will lose energy, and so also the position of the Bragg peak will shift. By the way, here on the left, you see the typical radiation field with X-rays. So you really see how much radiation dose is left in the surrounding of the tumor. And on the right side, you see what can be achieved with the protons, and it's even much better with ions. And these are realistic images, okay? So these are really extracted from medical publications. So now, what this has to do with the sensors, with the pixel sensors I've presented? Well, the issue, as I mentioned, is that to aim precisely the Bragg peak, you need to know the density of the tissues surrounding the tumor. And this is done at the present with X-rays. Okay, so you irradiate with protons or ions, but the imaging is done with X-rays. And this is absolutely unsatisfactory. It has really is the limiting factor at present. Okay, it introduces systematic errors up to 5%. That's the reason you see this image of this type. Okay. Now this could be improved if actually we could use also protons, also to do the imaging itself. Now the typical beam energy needed for a deep-seated tumor in the brain is of the order, depending on the position, but between 60 and 200 MeV. Okay. Now multiple scattering is a big issue at those energies. So there is a possibility of cranking up the energy a bit up to 400 MeV or so, but still the multiple scattering is the limiting factor unless you have a very thin detectors, okay? And the CMOS sensors have shown is what they can advance this significantly. And that's what we started doing. And we started with the silicon strip detectors, but these are too slow. And to take a picture, an image, a 3D tomography, this requires of good quality, about 100 millions of tracks. And this takes about 10 minutes at present. And during 10 minutes, even if the patient is still, the tumor floats. And so that is also a limiting factor. So there are two projects at present under development funded by the European Union, which are based on the silicon sensors that I've mentioned to you, which aim at reducing the time for building a tomography to essentially 10 seconds. Okay, so there's really a factor 100. And thanks to their very thin material, to their very low material thickness, they also reduce significantly the multiple scattering. Okay, so and with this, I would like to conclude. So I've shown to you the type of fundamental research we carried out at the ALICE experiment, a bit of our plans for the future. But in particular, I wanted to show to you, as I said in my introduction, that a lot of what we do has to deal with technology and technology innovation and development. So it's a really program which offers very interesting opportunities, not only for physicists, but also for the engineers in many different areas. Okay, I've shown the sensors, but I could have shown mechanics, electronics. It's a really a multidisciplinary approach. And I really believe that the high energy physics community is in a unique position to bridge between these different fields and drive the development in many different areas. And with this, I would like to thank you.
think, is it okay? We'll take a few questions.
I wanted to ask one question is that in run 2 CMS, we observed the top quark in the heavy ion collisions. So what is the status from the Alice side?
Okay, there we go. So, yeah, no, I think this is not within reach. Well, we will see, but not so sure that this will be within reach. But you think the CMS can do it in run 2? With the statistics you have? I mean, I've seen the paper, but yeah.
2020, we and second point.
I think, you know what, I don't want to escape your question. So I think that, well, in run 3 and run 4, we will be collecting all individual collisions, heavy ion collisions. So we will see what is possible. In my opinion, probably this will not become yet a mature probe to be used in run 3 and run 4. For Alice 3, definitely, okay. We have also made some estimate. And well, then at a future circular collider, that will be our ordinary probe, right?
And the second point I had was that, is there a reason for half depleted or partially depleted silicon?
Yeah. Yeah, very good question. Yes. So if you don't deplete it completely, you typically have the charge, which is collected, spreads over several pixels, and then you can achieve a better position resolution by applying a center of gravity algorithms, okay? You've seen there we have a pixels of 28 microns by 28, 27 by 29, and we achieve a spatial resolution which is better than 5 microns, okay? Which is, you know, it's not the pixel size divided by square root of 12. So that's the advantage. The caveat, of course, is that if you collect them, if they're not fully depleted, then the radiation damage is has a larger impact in attenuating the signal. So depending where they are placed, then you can decide to have them fully depleted in the innermost layers. You would like to collect them quickly and be less sensitive to the radiation damage. When you move a little bit out and the radiation becomes less important, you would like to increase the spatial resolution. And you know, for Atlas, there was also all this work on the fully depleted sensors. For the ATS3, we see that we can fully deplete easily. So that is really for the ATS3, we have measurements done which show that they behave all the way to 10 to the 15, 10 to the 16 neutrons, 1 MeV neutron equivalent per square centimeter. So they're really very radar by now.
Okay, so I must thank you for very interesting and nice talk. Yeah, as a chemist, I'm Vishnu Biswa. Okay, I'm faculty of chemistry department. So as chemist, I'm little curious that why you have chosen lead, okay, for your collision. Okay, because there are several elements. Is it because heavy or some other things are hidden?
No. Essentially, one tries to use the nucleus of a very large atom, the heaviest one, to have a very large number of protons and neutrons in the nucleus. Okay, so they're fully stripped, right? I mean, it's really the nuclei of these atoms. And by the way, we use lead, but at RIC they use gold, because in the US they're more fashionable.
Okay, so there is.
But we privileged a slightly larger number of nucleons. Okay.
Okay. Thank you.
For this beautiful talk, and also coming to India, spending time with all of us, not only at NISER, at other places. And also leading the ALICE experiment, and also coming up with this ALICE 3, which is the future for heavy ions. So as a token of appreciation, we would like to give you a memento, which is typical to this state. It is called Patachitra. It's a painting which is made in villages which are close by. And this state is rich in culture, heritage, art, dance form. So painting is also one of this. So I would request our director, Professor Sudhakar Pandit.
Thank you. Thank you, really. It's been a great pleasure. Thank you.
There is some IT, the colloquium ends here, so please join.
Oh, good. Very nice.
Yeah, this is এটা হলো আমরা কি না নেই কি বিজয় মথুরা বিজয়
Put it okay. Okay. Thank you. Okay, all right. Thank you. Sorry, I took a bit too long. Thank you very much.